on chapter 4, which is based on solutions in aqueous reactions, meaning stuff that happens in water. We did talk on Tuesday about both kinds of double replacement reactions. To quickly review, remember there's 3 driving forces for double replacement reactions. One of them is the insolubility of the products. Remember where we talked about the ions in solution? If they're soluble initially, they will go into solution. They'll break apart from their counterparts. Once they're in solution, that gives them the opportunity to react with each other. And what causes them to react with each other is 3 different things. First of all, solubility. If they see each other and they go, whoop, we're going to precipitate, that's going to promote a chemical reaction. That's visually, generally what you're going to see is a precipitate that gets a little bit cloudy in solution. You did that this week in your lab. The second thing you might make is water, which is an acid-base reaction. Did they talk in lab at all about how you tell if an acid-base reaction has occurred? You can't see water being formed, right? You put an acid and a base together. They're both clear, colorless solutions. And you know a reaction is occurring in there, but there's nothing visual. There's no precipitate like in the double replacement reactions that are driven by solubility. How do you know that acid-base reaction? Is there another way to measure? Yes? Gas. Good guess, because that's one of the driving forces for double replacement, but no, there's usually not gases produced. Yeah?
The pH meter?
That would certainly give you an indicator, because as the pH changes, you start with an acid, it's going to have a pH less than 7, a base is going to be greater than 7, at some point it's going to be neutralized. That's true. Beyond that, I don't want to say you're wrong, because you're absolutely right if we have a pH meter, but even something simpler than a pH meter.
Temperature.
Temperature. What happens when acids and bases come together?
Increase in temperature.
It gets hot. It gets hot, right? So acids and bases, putting them together, it actually gets hot. And one of the labs you're going to do in Chem 151 is you actually put an acid and a base together, you measure the temperature change, and you calculate something called the enthalpy of the reaction. So visually, you don't see anything when acids and bases react, but you can use a tool or your senses to determine if an acid-base reaction has occurred. That's why in the lab they tell you, okay, if you spill an acid or base on yourself, some people think, oh, well, I need to neutralize that, I'll just pour the opposite. That's never a good idea because it's an exothermic reaction, and the causticity of the acid and the base individually will harm you much greater than the availability of them to neutralize each other. So water is always the best solution to any problem. There's a solution chemist joke, water is the solution, right? Okay, with my bad chemistry jokes in the back pocket here, let's talk about these things. We already talked about dissociation. Dissociation occurs when things are soluble, right? Ionic compounds, you put them in water. If they're soluble, that means they'll break up, they'll dissociate, they break apart from each other. And that's because the collective attraction of multiple water molecules pulling on an individual ion is greater than the attraction that the individual ions have for each other. So that's why dissociation occurs. And we're going to talk about the energy changes in dissociation a little bit later in the course. Solutions are composed of a solute and a solvent. And when we discuss concentration of solutions, we use that as a ratio and proportion. And I can't stress how important it is to discuss about solution concentration. All right. When we have a solution, that means you have a solute that has been dissolved in a solvent. All right, if you look at those 2 words, those are going to be super helpful for us in this chapter to define what kind of a solution that we have. The solute is generally the thing being dissolved, right? And it's generally in the minority of concentration. Now, whenever you put little square brackets around something in chemistry language and lingo, that means concentration of. So the thing that is the solute is usually the thing that is lesser in proportion, if you look at the ratios and proportions. The solvent is the thing that's doing the dissolving. And they call water, good old H2O, right, dihydrogen monoxide, they call it the universal solvent. What do you suppose that means? What does that imply? The universal solvent. It'll dissolve dissolve almost anything. So most ionic compounds, and when they say this, it's kind of a chemist thing. It means that most ionic compounds are soluble and will dissolve in water. So they call water the universal solvent. However, there are things that water will not dissolve, things like oil or grease or things that are non-polar. And when you get into organic chemistry, there's weeks and weeks of discussion about that. All right, so solute versus solvent. We use lots of different ratios to compare. A very simple ratio might be grams per liter. You might see something like that in a consumer product that you consume, but that's not as helpful to chemists as a different way to measure concentration. Does anybody remember the unit that chemists like to use that compares this idea, the solute to the solvent?
Molarity.
Molarity, right? Molarity is the one that we tend to use most often, and molarity is symbolized by capital M. And what is the definition of molarity as a concentration value?
Moles per
It's
milliliter.
the moles per liter. So what that actually means, when you're thinking about the molarity, is the moles of the solute, because remember, all concentration units are a simple ratio of solute to solvent, divided by liters of, in this case, solution. So moles of solute divided by liters of solution. And this is far superior to a unit like grams per milliliter. You might see some concentration units that are very simple in consumer products, grams per mil. And that's helpful for things like sodium or sugar. You want to know how many grams of sodium or grams per sugar there are in whatever it is that you're consuming. But that's not as helpful to us as moles, because moles then connects the balanced chemical equation. And the balanced chemical equation tells you how many pieces of reactants and how many pieces of products you have, and that's where moles is so much more helpful and so much superior in terms of its availability as a unit of concentration. All right, so solutions are all homogeneous mixtures that are composed of a solute and a solvent, and all of the different concentration values, and we're going to talk about quite a few of them today, all are simple ratios of what you're dissolving compared to what you're dissolving it in. All right, so that's what you have to remember. And electrolytes. You know, they talk in popular media about electrolytes. What does electrolyte mean to you when they're talking about TV? On TV, they say there's a popular sports drink that's supposed to replenish your electrolytes. Gatorade or Powerade. Okay, what does that have? Have you ever looked at the back of a bottle of Gatorade or Powerade?
Sugar.
A whole bunch of different salts, right? Remember, salt to a chemist is simply a metal-non-metal combination. The majority of the chemicals you're going to come into contact with in the lab are going to be salts. They're ionic compounds. So you can look at the back of a Gatorade bottle and it has magnesium compounds, magnesium salts, sodium salts, potassium salts. Those are all important salts, especially sodium and potassium salts for our blood chemistry. To help the synapses in our brain as well as our bodily organs function, we have to have electrolytes, because why are electrolytes important in our body, and why are electrolytes important in aqueous solutions in chemistry, first of all? What do they do? What do electrolytes do for us? In a solution, if I said I have a solution that is an electrolyte, how could I prove to you it was an electrolyte?
Have electricity.
If it would conduct electricity, I could have what's called a conductivity apparatus, and it's a little light bulb connected with like a battery and terminal, you know, positive and a negative, a cathode and an anode. And when you put this little apparatus, I think there might even be a picture of it in the slides here. There we go. There's the conductivity apparatus. And you put the electrodes, the positive and the negative electrode, in a solution, and if the solution contains ions, then the light bulb will light. If the solution does not contain ions, then the light bulb will not light. The ions in the solution cause the electricity to be able to move through the solution. So theoretically, and I'm going to put this in air quotes, theoretically, right, if you had a bathtub full of distilled water without any ions in it and you dropped the hairdryer in it, would you be okay? Theoretically, right? Theoretically. But we don't want to do that, because water has what we call the self-ionization of water. It's always making hydrogen or hydroxide ions. So even in distilled water, there's going to be ions in it that will conduct electricity. In order to get pure water without any ions in it, you have to make sure that it's called ultra-pure water. We can get it in the chemistry lab. It never touches air even, because air tends to add ions to it. So theoretically, if you had a bathtub full of distilled water and there were no ions in it, you could drop a hairdryer. But don't do this at home. right? Do not do that. You will get electrocuted. But the idea of electrolytes, and so electrolytes, we drink them in things like Gatorade, or it's important for us to have sodium and potassium salts in our body because it helps electrical impulses go through our body. Our heart has to have an electrical impulse to beat. Our blood system has to have electrical impulses to pump it through. Our brain synapses have to have electrical impulses. So one of the first indicators of dehydration or low sodium or low potassium is you go a little wacky. Your brain doesn't work right. You know, you start going a little crazy, and sometimes it's simply low potassium or low sodium that is the issue. So electrolytes are important to human beings, but electrolytes are also important to chemists. We can tell how many ions are in a solution by measuring the conductivity of the solution. So you can have a conductivity meter and you put it in, the light bulb glows really light, or the conductivity measures a whole lot of electricity being generated. Or if you put it into a solution that does not have any ions or has just a few, it might just light up a little bit and the conductivity meter might just barely move a little bit. So you can measure the relative amount of ions in solution by using something like a conductivity meter. So a strong electrolyte is something that has lots of ions in solution. A weak electrolyte is something that doesn't have many ions in solution. And that leads us to the definition of strong acids versus weak acids. Anything that's a strong acid, a strong base, or anything that's soluble, and there's why we have the solubility rules available to us up on the screen, is any of those things are going to be what we call strong electrolytes, meaning when I put them in water, they're going to completely dissociate into their component ions. Almost 100% of them are going to break up in the water and make ions. So for example, I'll use some numbers here to give you some examples. If we're talking about concentration, say for example I have a strong acid. Oh, by the way, there are 7 strong acids and you should know what they are. I think they're on this PowerPoint slide, if I'm not mistaken. One of those is in there. Let's see. There it is. There's the strong acids. Hydrochloric, hydrobromic, hydroiodic. Where are those? Where do you notice those anions on the periodic table for the hydrochloric, the hydrobromic, and the hydroiodic? They're the halogens. All right. So the acids that make up the halogens, the 3 below fluorine, are all strong acids. Hydrofluoric is the only one of the halogens that makes a weak acid. So there's a mnemonic device that will help you. You will need to know the 6 strong acids for the next exam. And you will also need to know that of the 6 strong acids, those are the only ones that are strong. Everything else is weak. Now we'll talk about weak acids in a minute, but right now I want to talk about strong acids. So those are the 6 strong ones. So when I put them in water, they dissociate completely. So if you look at a periodic table, there's hydrochloric, hydrobromic, hydroiodic are all strong acids, meaning when I put them in water, 100% of them break up into hydrogen ions and their component anion. The only one that is not true of is hydrofluoric acid is considered a weak acid. Now, why would that be true? If we could look at a periodic table, let's see here. Look at a periodic table. All right, here's hydrochloric, hydrobromic, hydroiodic. Those are all strong acids according to our chart. Hydrofluoric is a weak acid. Now, if they're all the same group, they're all halogens, right? They have how many valence electrons if they're in group 7? 7 valence electrons. Hydrogen then is held by that halogen. So chlorine, bromine, and iodine, when they make acid, it's real easy to break them up. You put them in water, bing, they're broken up. How come it's so hard to break up hydrofluoric? Why is it only a weak acid? Why is it only maybe 5 or 10% of the hydrofluoric that we put into water breaks up? What's different about fluorine compared to chlorine, bromine, and iodine? Say that again?
Mass.
That's part of it. Part of it has to do with the mass, but another physical characteristic of fluorine that's different than the same family.
Oh, it's diatomic.
Actually, I think all those are, but we're not talking about the gas right now. We're just talking about it as an acid. Good guess. Somebody in the back there? Well, sort of the same idea as mass. That does have something to do with it, but I'm looking at a different reason. And you're right. Those are true things. It has to do with the size. Who's biggest of that family? Fluorine, chlorine, bromine, or iodine? Who's the biggest? Who would have the largest radius? Iodine. So remember, it's the valence electrons that are holding a compound like an acid together. So the valence electrons of something like iodine, when it's holding on to hydrogen, are really far away, right? Because it has a whole, how many shells does iodine have? 5. It's got 5 because it's in the row 5, right? So that means it has 5 shells of electrons. So the valence shell is way far away from that nucleus. And so it's really easy to take that hydrogen off because it doesn't feel that positive pull of the nucleus quite as significantly. So bromine and chlorine are also fairly large. So that bond that they make with hydrogen in the valence electron is very far away from that positively charged nucleus. So it's easy to take that hydrogen off. But then we look at fluorine. How many shells of energy levels does fluorine have? 2. Only 2. So that hydrogen ion that's hooked on by the valence shell in fluorine is held much tighter. And so it's real hard to pull that hydrogen ion off. And that's what makes it a weak acid. So when we write what are called dissociation reactions for strong versus weak acids, to my ladybug here, if we look at something like HCl, which is one of the strong acids, we use what's called a completion arrow, which has the bar but only on one side. And we say HCl, when it's in aqueous solution, makes hydrogen ions and chloride ions, both of which are now in aqueous solution, right? H2SO4, also a strong acid. We use a completion arrow for. Now it's not H2, it doesn't make hydrogen gas. No, when it goes in aqueous solution, you have to remember that it's making 2 of those hydrogen ions, not H2 as a gas, right? So put that in your notes. It's not H2 as a gas. It's 2 hydrogen ions plus the SO4, which is the polyatomic ion in aqueous solution. So these are strong acids. So strong acids, we use what's called the completion arrow. So that means every single piece of stuff that we start with is going to react, or is going to dissociate and create only these things in solution. So once I have an acid in aqueous solution, no more do I have the undissociated major particle. I have only those things in solution or only those things in solution for strong acids. So strong acids are strong electrolytes because every single one of them that you put in breaks into ions. And the more ions you have, the stronger the light will light. If we look at something like a weak acid, if you know the 7 strong acids, every other acid is a weak acid. How do I know that this is an acid right here, whatever? It starts with a hydrogen, and it's got some polyatomic anion. In this case, this is acetic acid. You're going to see a whole lot of acetic acid when you get to Chem 152. There's literally like 2 chapters full of discussion of acetic acid. So when you talk about acetic acid is a weak acid. It only partially dissociates. Here, 100% dissociates. Right? 100% of strong acids dissociate. Weak acids, maybe 5%. So just a few. And we use what's called an equilibrium arrow. EQUIL, equilibrium arrow. Which means that, yes, we have some of these things that break up into their component ions, of course, in aqueous solution. But if you looked at a container of acetic acid, you would have all 3 things in there. You'd have a whole bunch of the undissociated. You'd have 95% of everything you had in the beaker, once you put weak acid into a beaker, is going to be the undissociated molecule. Only 5%. You're only going to put really little, right? To signify that our concentration of the ions would only be approximately 5%. So if I put a conductivity apparatus into a solution that was a weak acid, it would only glow a teeny tiny bit because there's only 5% as many of the ions in solution for a weak acid as there is for a strong acid. This translates into concentration really well, and this is just big picture ratio. So if I have a 3 molar solution, and there's my concentration, I'm putting it in a the square brackets, if I got a 3 molar solution of hydrogen or hydrochloric acid, what's going to be my concentration of hydrogen ions there?
3 moles.
It's going to be 3 molar. What's going to be my concentration of chloride ions? Is it not also going to be 3 molar? So my concentration of ions in solution would be,
Equal.
no, all ions would be 6 molar. So you would have a total concentration of 6 molar ions. So total concentration is 6 molar in the solution. Let's look at this acid. If I started with 3 molar of this stuff, right, put this stuff in, think before you answer, what would be my concentration of hydrogen ions?
6.
It'd be 6 molar, right? So it'd be twice as much because for every one of these that breaks up, I get 2 of those. What would be my concentration of sulfite ions? 3 molar. Turns out this is a super simple concept, right? But it's super crucial for you to understand this because what is the definition of pH, which is how we measure the acidity or basicity of a solution? Does anybody know the definition of pH? Has to do with the number of hydrogen ions. It's the negative logarithm because it's a gigantic range, and logarithm shrinks down the range to a manageable number, like 14. It's the negative logarithm of the hydrogen ion concentration. So when you have a strong acid that's has 2 protons to donate, the concentration and the pH are going to be very different, right, based on that definition. We're not going to talk about pH yet, not until one of the very end chapters of this class, but I wanted you to see that that was important. Here, you know, if we had a concentration of 3 molar here, right, it would only be 5% of 3 molar, which is like 0.10 molar of hydrogen ions. So you have a much smaller concentration of hydrogen ions in a weak acid. All right, so all of the strong acids are strong electrolytes. All of the ionic substances that are soluble are strong electrolytes. All of the strong bases are strong electrolytes. There is a trick to remembering the strong bases. It's just like the strong acids. If you know the 6 strong acids, everything else is weak. If you know the strong bases, everything else is weak. The trick to remember the strong bases are, once again, we got to get our periodic table up here. Here we go. It's, how do you know, first of all, that something is a base? If you look at the formula for a substance and you say, yep, that's a base, how do you know?
Hydroxide.
It's got hydroxide on it, but it has to be a metal hydroxide. You can have a non-metal hydroxide, things that are non-metals hooked up to hydroxide, and that's called an alcohol. And you'll discuss those things when you get to organic chemistry, but you must have a metal hydroxide is a base. So you have to look at what metals could potentially hook up to hydroxide to make a strong base, and it's any of the alkali metals. So lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, or cesium hydroxide are all strong bases, which means once you plunk them in water, what do? Dissociate completely. 100% of all the pieces you put in completely dissociate, so you can bank on that. That's important information. So any hydroxide that's hooked up to an alkali metal is a strong base, meaning it will dissociate completely. The heavier nonmetals of the alkali earth metals, meaning calcium, strontium, and barium, are also the strong bases. So quickly review. Hydroxides of the alkali metals, all strong bases. Hydroxides of the heavier alkali earth metals are strong bases. If you know the strong bases, everything else is weak, right? All right, so strong bases are also strong electrolytes. Precipitation reactions. We just discussed this last Tuesday. We talked about double replacement. I'm not going to go through these. These are all in the PowerPoint. For sure, you should know how to write net ionic equations. That's part of your homework assignment that's due on Tuesday. I only ask you to write a couple of them, but keep in mind, if you need more practice, you can go at the end of the chapter and look for net ionic equations to write there. Your lab would be an excellent way to practice. I was a little disappointed to find out their lab teacher's not asking you to write net ionic equations for your metathesis reactions. I would personally, if I was teaching lab, I would ask you to do that because it's also good practice. So if you want extra practice, since you will have to do that on the next exam and on the next quiz, it's a good idea to practice those kind of things, and the lab would be the perfect time to do it. All right, so we already talked about acids. There's 7 strong ones. Sorry, I said 6 strong ones. There's 7 strong acids. There they are. Bases, if you've got a metal hydroxide. So there we talked about calcium, strontium, barium, or all the alkali metals are the strong bases. Acid-base reactions, you always get salt and water as a product, right? And we already did neutralization reactions on Tuesday, and you had lots of good examples of that. The third driving force in metathesis or double replacement reactions is this idea of gas-forming reactions. We don't see a lot of those in this class. You discuss these a little more significantly when you get to Chem 152 because these are what we call multi-step reactions, meaning they don't happen as written. What happens is the reactants react, they produce some intermediate that then has to react with other things and produces the product, and the intermediate cancels out, sort of like in algebra when you're combining equations, and this is sort of the end result of the equation. As you can see, the gas-producing ones, it's either, bless you, it's either CO2 is the gas that's produced or SO2 is the gas that's produced. And in that case, the driving force is the gas being produced rather than solubility or water, right? So remember, metathesis reactions, the three driving forces, solubility, meaning the formation of an insoluble product, a precipitate, water being formed if it's acid-base, or gas-forming ones in which those are the majority of the types that you're going to see. Okay, which leads us to redox reactions. I'm going to go because I find that using examples is much more helpful than just going through the PowerPoints. So we're going to talk now quickly about redox because that's the ones you're doing in lab this week, right? And hopefully you're talking about the oxidation reduction aspect of redox reactions. So there's two types of redox reactions, big picture ones. They're all driven by the activity series. One of the biggest misconceptions in this class as well as Chem 130 is students mixing up single and double replacement reactions. All right? Easy to mix up. They're very similar in the way that you write them. They both have spectator ions, but they're driven by two completely different reasons for the things reacting. Metathesis reactions are driven by the driving forces, the three driving forces. Redox reactions are driven by a single idea, and that is the activity series. So activity series is what you use to determine if a reaction will happen when you take a metal and you put it either in an aqueous solution that is a salt, put that in quotation marks, remember salt is anything that's ionic, or an aqueous solution that is an acid. Okay? So a metal in an aqueous solution that's a salt, or a metal in an aqueous solution that's an acid. All right, let's talk about a metal in an aqueous solution that's a salt. So let's talk, I like aluminum. I know this one will react. We could put it into a solution of copper chloride. That's CuCl2, not CaCl2. Cu, I didn't write that very good. CuCl2. All right, what would have to be true in order for this reaction to occur? Right, aluminum would have to be more reactive than copper, and it is if you look at the activity series. So it would replace copper. So what would be my products in this case?
AlCl3.
We would have aluminum and chloride would now be in solution, but now the key with these redox reactions is the charges change. Remember in metathesis reactions, writing the formula for products was easy because the charges were the exact same as they were when they were reactants. That makes your life easier. Now electrons are flying around. The charges change. So you've got to rewrite nomenclature based on your common experience and what you know about the ions in question. So now what do you know about aluminum in terms of its ionic charge when it goes into aqueous solution? It's +3. What is true of chlorine when it goes into aqueous? -1. So what is the correct nomenclature for aluminum chloride? All right, so it doesn't retain. Now, remember when a metal is in its solid state, what is its charge? 0. So I never want it. One of the common mistakes that students make in this class is they think, oh, aluminum's always +3. And so they start throwing a +3 next to aluminum. When you see S, that means it has all the electrons it was born with and it has no charge. Okay? Only when it goes into aqueous solution does it lose electrons and then get some charge. Bless you. All right, so this is an aqueous solution now. And what's my solid metal that comes out of this? Copper. Copper solid. All right. So if we go back and we start looking at what are called oxidation numbers. Oxidation numbers are the same thing as the charge on the ion in the compound. So you got to go through and look at all the oxidation numbers. Anything that's a metal in solid state has oxidation number of 0. Okay. Now we know that this is an aqueous solution, so these are ions. We don't know the charge on copper because it's one of those elements that doesn't always have a particular ionic charge, but we do know the charge of chlorine. What's the charge of chlorine?
Uniform.
-1, and if we divide this in half, and each of those chlorines is -1, and there are 2 of them, what must that half be? -2, so this half has to be +2 to balance it out, and since there's only 1 copper, what does that 1 copper's charge have to be? +2. Alright, so now, we know what the charges are, but we still have to balance this. How would I balance this thing?
2AL 3C02.
I think that's a good idea, because when we got a 3 and a 2, we want 6 on each side, so 2 times 3 is 6. So then a 3 there, so I have to fix that, and then that, right? And our equation is balanced. Alright, so now we gotta do the redox part of this, and you go, alright, who was giving up electrons, who was taking them? And I hope that your teachers, are your teachers showing you how to do this in lab?
Not like this.
Okay, when you get to Chem 152, this is going to be a skill that they expect you to have in your back pocket. There are 8 chapters in 152. One of the 8, so fully 1/8 of the course is electrochemistry, which is all redox. So you got to know how to write net ionic equations, and I will test you on this. So my suggestion to you is use the reactions you saw in lab and write some redox and some net ionic and half reactions with this, which is what I'm going to show you how to do right now. All right, so aluminum changed, right? And copper changed. So actually, you know what, even before we do that, we could write the ionic equation. I'm not going to erase that because that's a good visual. Let's write the ionic equation. That one is a solid, so it just stays as is. 2 aluminums, solid. Now since it's an aqueous solution, we use the same rules as we did in the metathesis reaction. We've got to break up that whole thing and show how many ions were in our solution. Plus 3 copper ions, each with a +2 charge in aqueous solution. So does everybody see where I got 3 copper ions, each with a +2 charge? Alright. 3 times 2 means I'm going to have 6 of those chloride ions also in aqueous solution. Now, I still have more aqueous solution stuff going on here, so I have to break those up. So if I break up 2 of those aluminum chlorides, I'm going to have 2 aluminum ions, each with a +3 charge in aqueous solution, right? How many of those chloride ions would I have? 6 chloride ions, also in aqueous solution, plus my 3 copper solid that I have. Now, metathesis reactions have 2 spectator ions, double replacement, that makes sense, right? 2 things are replaced, so there are 2 spectator ions. Single replacement reactions only have single spectator ions. So who is the single spectator ion in this case? 6. Alright, one of the big mistakes people make is they try and make this be a precipitation reaction. And they go, oh, I'll bet aluminum chloride is insoluble. And they find that they look at their solubility rules, and if they're interpreting the solubility rules correctly, they'll go, oh, well, it is soluble. But then they want to make it a precipitation reaction. So recognize single replacement versus double replacement are very different, and don't confuse the 2. So our net ionic equation then would just be 2Al solids plus 3 copper ions in solution yields 2 aluminum ions in solution plus 3 copper solid. I'm going to do my redox half reactions based on this one down here, even though we started it up there, just because it is a little easier to see because there's not so much clutter with the other stuff going on there. All right. So we know that aluminum, when it's a solid, is 0, and copper, when it's a solid, is also 0. So we're going to say, all right, we took 2 aluminum ions with a 0 charge, solid state, and they changed to 2 aluminums with a +3 charge in aqueous solution. I'm going to write this half reaction here. 3 copper ions with a +2 charge in aqueous solution yields 3 copper atoms with a 0 charge as a solid. So did I write that right? Yes, I did. Okay. So now here's how I think of it when I'm writing the redox half reactions. And when you get to Chem 152, not only are you going to have to write these redox half reactions, but then you have to do what's called balancing them in solution, which requires a whole bunch of more math and stuff in it. So that's why it's important that you have exposure and you have this skill prior to getting to Chem 152. If you look at a metal in solid state, it has all the electrons that it started with. When it goes into aqueous solution, it has lost some of those, right?
Mhm.
So if we think about aluminum, each piece of aluminum, what did an aluminum atom over here have to do to become an aluminum ion on the product side?
Lose 3
Had
electrons.
to lose 3. So I want to show that in my half reaction, because this is the thing that had all the pieces it started with. Once it breaks up, I'm going to show the pieces that it breaks up into. And so if each aluminum atom had to give up 3 electrons to become an aluminum ion, and there were 2 aluminum atoms, each of which lost 3 electrons, how many total electrons would be lost?
6.
6. So I would put the 6 electrons on that side. Because once again, that's the thing that has all the pieces it was born with, and those are the things that it breaks up into. So remember, on my device, there's another one, Leo the Lion goes grr, but I like whale rig. Oxidation versus reduction. Oxidation is the loss, reduction is the gain. So what's happening here? Is this the oxidation half reaction or the reduction half reaction? Good, because that's losing it. So that's the oxidation, what they call half reaction. Alright, conversely, let's look at copper. Now if we look at an individual copper ion on the reactant side here, what did an individual copper ion have to do to become a copper atom on the product side? Had to gain. How many did it have to gain? 2. If I have 3 particles of copper, each of which gains 2 electrons, how many total electrons are gained? 6. Would I put those as being on the product side or the reactant side? Reactant side, because you had to gain them on the reactant side in order to become this thing that had a 0 charge, which once again goes against your algebraic training. Because in algebra, when you gain stuff, you generally become more positive, right? When you lose stuff, you can become more negative. Well, in redox, it's opposite. You gain electrons, you become more negative, right? You lose electrons, you become more positive. All right, so a good way to double check that you're doing these right. The initial equation has to balance. The ionic equation has to balance. The spectator ions, when you cross them out, have to have the same number. The net ionic equation has to balance. And then when you're looking at the half reactions, electrons gained has to equal electrons lost, and they have to be on opposing sides of the equation. Right? Alright, so that's the first kind of redox reactions, where we have a metal in aqueous solution that makes a salt. Now I want to do a metal that's in an acid aqueous solution, because it's a little bit different kind of an animal. Alright, so let's try a metal that's pretty reactive, like, they have their activity series. I know magnesium's pretty reactive. Let's pick magnesium. And we'll put magnesium into some strong acid. We'll put it into hydrobromic acids. Alright. In order to determine if this reaction will occur, and I got a metal in an acid, what would I have to compare? What would I have to look at? What's the name of that table that will tell me if this activity series? And what would have to be true on the activity series in order for this reaction to occur?
The magnesium.
The magnesium would have to be more active than hydrogen. Remember, hydrogen, even though it's considered a non-metal, is still in the activity series because we've got to deal with acids. All right, so it is, so it will replace. So what's going to be one of my products? Magnesium bromide. So now we have to figure out new nomenclature. And if we look at magnesium on the periodic table, it's in group 2, so what's the charge on magnesium going to be? Plus 2, and bromine is -1, so what's the nomenclature for magnesium bromide? Br2, and that's going to be our aqueous solution. And what else am I going to get out of this? Hydrogen gas. And what's the formula for hydrogen gas?
H2.
H2, not 2 H's. H2 gas. And so in this case, what you would see would be bubbles, right? In this reaction, you would see, what you would actually see, and this is important to see, we have our solution of the copper chloride, so we have copper ions and chloride ions floating around. We drop a hunk of aluminum in there, and where the aluminum was touching the liquid, it would start to get kind of fuzzy, and the stuff would grow on it, and the fuzzy stuff would start to sink to the bottom. And the fuzzy stuff would be kind of copper colored. What would the fuzzy stuff be?
Like
Copper. Alright, so that's what you would see was the stuff would be growing on the surface of the aluminum. It would look, and why that's actually happening is because that's where the electrons are flying around. The aluminum is giving up some electrons, right? It's going into aqueous solution, and who's grabbing these electrons? Not chlorine. Chlorine's a spectator. Copper's grabbing those electrons. And so that's why it's able to form a precipitate, and it's making a solid, and it's coming out of the solution, so you would see a little pile of copper metal at the bottom of the container over a period of time as the copper was generated. Copper ions also create a blue colored solution, and because you're taking those copper ions out to make a solid copper precipitate, the solution will become less blue. So I know that you actually do some reactions with copper ions in solution. When you notice the solution is becoming less blue, that's because you're taking those copper ions out of solution, which causes it to have that blue color. In this case, what would you visually see happening in the container? When you dropped a hunk of aluminum into some hydrobromic acid, what would start happening? Bubbles. You get lots and lots of copious bubbles. And what would those bubbles be made out of?
Hydrogen.
How could we prove they were made out of hydrogen?
Light on fire.
Light on fire. What would happen? We would have a little minor explosion, right? You can actually capture a test tube of hydrogen over a reaction like this as it's happening. You can capture it. You pass a lit match under the test tube and it goes whoop, and it'll make this really cool like little mini explosion. If you take a larger piece of glassware and do it, you can get even better explosion. Don't do this at home. Just as an aside, chemistry is not for amateurs, right? Okay, so even chemistry teachers blow themselves up. That's another story. Okay. Now we want to look at, we haven't balanced this one yet. So what do we got to do to balance this thing? 2 there, and that takes care of the hydrogens, and also takes care of the bromine, so I think it's good there. Alright, so let's write our ionic equation, which would be Mg as a solid, plus, when I break up 2 of those HBRs, what am I going to get? 2 hydrogen ions in aqueous solution, not H2, right? Because aqueous solution is different than gas. Plus, what else? 2 bromine ions, also in aqueous solution. So now, because it's also an aqueous solution, I'm going to have a magnesium ion now, with a +2 charge in aqueous solution, plus 2 of those bromine ions, also in aqueous solution, plus my H2 gas. All right, in this equation, what is my spectator ion?
Magnesium and bromine.
No, magnesium is not this. That's like saying I can cancel x squared on one side and 2x on the other, right? Spoken like a former algebra teacher. Remember, any kind of metal has a 0 charge. That's not the same as an ion in solution, so you can't, even though in algebra it might look the same, it's not, so you can't cancel those. This is not the same either, right? Now, in algebra, this would be 2x versus x squared, right? You can't cancel those on the second equation, but they're very different animals. One's a gas, one's an aqueous solution. This is a solid, that's an aqueous solution, so they're definitely not the same. What is the same? Bromine. So there's our one spectator. Remember, single replacement only has a single spectator ion. So now we rewrite, we get our net ionic equation. This would be a good one to practice your lab reactions for. Alright, so now we wanted to do our redox half reactions. We say, alright, magnesium has changed. Hydrogen has changed. So let's write our redox half reaction. We got Mg solids that changed into Mg with a +2 charge in aqueous solution. And 2 hydrogen ions in aqueous solution that changed into hydrogen gas. Alright, let's copy that down. Well, so far they're all balanced, so we're good there. We look at magnesium solid. Remember, it has a 0 charge here as a solid metal. What did a single magnesium atom have to do to become a magnesium ion? Lose 2 electrons. So where am I going to put those electrons, on the reactant or the product side? Product side, plus 2 electrons. Now here's where it gets a little sticky. What did a single hydrogen ion have to do to become part of this hydrogen ion, or this hydrogen molecule, which, remember, all the diatomics, there's one more thing to remember about the diatomics, they all have a net charge of 0. So what did this single lonesome hydrogen ion have to do to become part of that hydrogen gas molecule? Had to gain 1 electron, right? That single hydrogen ion had to gain 1 electron, but if I got 2 hydrogen ions, Each of them gains 1 electron. How many total are gained? 2. So we want to put that on the reactant side, all right? So now, remember oil rig? This is something you will have to do on your next exam. Which one of these was the oxidation half reaction? Good, so this was the oxidation half reaction. So that means this is the reduction half reaction. All right, well, that's about as fun as that's gonna get. All right, so oxidation reduction. Here's more good stuff about oxidation reduction numbers. We've already done oxidation numbers. A neutral compound, the sum is always 0, so ionic compounds, that's what you can always count on. If it's a neutrally charged ionic compound, it won't have a charge associated with it. If it has a charge associated with it, it means it's an ion. Generally, it's going to be an ion in solution. So the sum of all the oxidation numbers in a polyatomic ion is the charge on the ion, so everything that you add up together. For example, if we look at something like NO3, well, you know what, we'll go into that a little bit later when we get deeper into this. All right, so there's some good demonstrations of what they look like. They're kind of cool. Certainly go out and watch them on YouTube. And we've already done oxidation reduction reactions, both with acids as well as with ionic salt. So there's the activity series that you should be able to use. We already defined molarity as moles of solute divided by liters of solution. And now we need to talk about when we're mixing up a solution, how that might actually translate and how the numbers that you would need to calculate. All right, so let's go through and do some examples with this idea of molarity. So, units of concentration. There's molarity, which is moles per liter. There's molality, which is moles of solute divided by kilograms of solvent. Remember, concentration is always a ratio of solute to solvent. So big M is molarity. That's one we use most often. Little m is molality. And this is used when temperature could influence the concentration of a solution. Molarity is temperature dependent. So what would temperature change out of moles per liter? The heat jump up. Is it going to change how many pieces are in there if you heat it up? No, not really. Is it going to change the volume of the solution? A tiny bit, a tiny bit. Water will expand a little bit when it's heated. And so if temperature is an issue in a particular reaction, then generally chemists like to use molality because it has to do with moles of solvent, which is still the number of pieces that you have of the original stuff you're dissolving, but instead of the volume, it's the mass of the solvent rather than the liters of the solution.
So then molality would be independent of temperature?
Yes, so it's temperature independent. Somebody had a question. I saw a hand back there. Young man. You good? Okay, that's what the question was. All right, so that's molality. There's also percent by mass. And so since percent is always part over total times 100, how would percent by mass be related if we're talking about a ratio of the solute to the solvent? What would be the part if we're talking about percent by mass? It would be the mass of the solute, right? And what would be the total? Not just the solvent, but the mass of what?
Solution.
Solute plus solvent. That's something to remember. Right, so there's the three major units of concentration that we use depending on what it's going to be useful for. All right, let's try an example. Something super simple, like let's try some good old. Let's try calcium chloride in water. All right, so I'm going to take 12 grams of calcium chloride in 750 mils of water. Let's calculate some concentration units based on that information. Well, first let's calculate the molarity of our solution. What would the molarity be if I got 12 grams of the junk in 750 mils of solution? What has to be first? Okay, so I have to convert grams to moles, so 12 grams of the calcium chloride. I have to go from grams of calcium chloride to moles of calcium chloride. And let's see, calcium weighs 40.1, and chlorine is 35.5 each, so that's 71 for the chlorine. 111.1, that's an interesting number. All right, what's 12 divided by 111.1? Somebody with a calculator.
Point one oh, or point one one, if you're rounding first.
Okay, so 0.11, good sig figs, 0.11. And what are my units here? Moles,
Of calcium.
okay, right, so far, moles of the calcium chloride. But that's not my concentration, is it? No, because molarity is moles per liter, so I got the moles now. Now what do I need?
Liters.
I need to get liters, so what's 750 mils in liters?
0.75.
Actually, I think it's 0.750, right? So if we take 750 mils, I can never do this in my head like you engineers do, I'm gonna do it. Right, okay, so that's right, so it is 0.750. Alright, so somebody with a calculator, what's 0.11 divided by 0.750?
144.
144?
Yeah.
So capital M, and I would say maybe even with sig figs 0.14 capital M. That means I've got 0.14 of a mole of this stuff for every liter of solution that I have. What would be the concentration, since this is completely soluble, or if it was, I'm not sure if it is completely soluble. If it was completely soluble and I put ions in solution, what would be the concentration of my calcium ions in solution? This is my concentration of the whole solution. What would be just the calcium ions?
0.14.
0.14. What would be the concentration of the chloride ions in my solution?
0.28.
0.28. You see how that works?
One more time.
Okay. One more time. If the concentration of my whole solution is 0.14 molar of this stuff, right? That stuff in solution, and I know when I take that stuff and I dissociate it, I'm going to get one of those and two of those, right? So if this is 0.14 molar, that's got to be 0.14 molar, and that's got to be 0.28, because why? Why is that 0.28 molar? It's twice as much. So what would be the total concentration of all my ions in solution?
0.42.
Whatever 0.28, 0.14 is added together, right? Okay. All right, so there's molarity. Let's try molality. Molality is a little bit different. Molality's baby M is moles of solute per kilogram of solvent. Now, in this case, let's say water was not our solvent, because water's density is 1 to 1. That confuses people because often then molality comes out for the same definition. So let's pick something with, we dissolved, we'll say we took our calcium chloride and we dissolved it in alcohol. All right, so, and the alcohol we dissolved it in was isopropyl alcohol, which is this stuff. And we'll just say, no, that's methyl alcohol. So we dissolved it in methyl alcohol, and it was still 750 milliliters of the methyl alcohol. But the density of alcohol is 0.93 or so grams per milliliter. So, if molality is our definition, and we want to get moles of solute, I think we already figured that out, didn't we? Don't we already have moles of our solute?
Mm-hmm.
Okay, so we can just use that, 0.11 moles of the calcium chloride, so molality is 0.11 moles of the calcium chloride. But now we need kilograms of our solvent, and if our solvent is 750 mils of this stuff, what am I going to do with that information? I got to use this number, which is a density, and it'll get me from volume to mass, right? Density gets you from volume to mass. I've got volume here, I need mass. So I'm just going to do a simple conversion. So you're going to take 0.750 milliliters, and you can set this up as 1 milliliter is 0.93 grams, right?
Yeah, I don't think it's 0.75.
Because it's like.
Oh, I'm sorry, I wasn't, you're right. So then what's this with a calculator? Just less than 750 grams. How much is it? 697.5. So we'll say 698. We'll say this was 3 sig figs since we had decimal, that zero's happy. So we'll say 698 grams. All right, now what do I do with that information? I gotta take 698 grams and I gotta go from grams to what? Kilograms. What's bigger, a gram or a kilogram? Kilogram. How many grams in a kilogram? So you engineers, you can do this in your brain. A simple chemist, we can't do that. We need to write stuff down. So 0.698 kilograms. Now what do I do with that? I take it up here, right? Because molarity is moles of solute divided by kilograms of solvent. That is my solvent, in this case the alcohol. So 0.698 kilograms. And what does that give me? 1.5 molality. And that's little baby m, not big M, it's baby m. Alright, if we were going to do percent by mass, that's a really easy one. We'll do it with the beginning, our numbers here from beginning. So percent by mass would be what? Super easy on this one. It would be 12 grams of my solvent, or solute, excuse me, will be the mass of the total solution at this point. Well, water has an interesting characteristic. For every milliliter of water, what is the mass?
1 gram.
1 gram. So that's nice. So that's a nice, easy conversion. And it's only true of water. And that's why I showed you the alcohol example, because alcohol's density is a little bit less than water, right? Alcohol's less dense. So this is how many grams of water? 750, which is how many kilograms?
0.75.
0.750. So wait a minute. That's not kilograms. We want mass. So we want 750 grams plus what else? Plus the 12. So it's 762 times 100. We're giving me percent by mass. Right? All right, those are the basic concentration units that you'll be using in here. Now we're going to take those concentration units and we're going to do something with them. If you were working in the lab, and after this class, you could actually get a job in the lab here at CGCC. In fact, they're looking for a lab tech. So once you're through with this job, keep an eye out on, because you might have to actually make a solution. If I said, all right, lab tech, I want you to make me a solution. I have to do a lab with my students, and I need 1.25 liters of a 0.85 molar solution of lead nitrate. All right. So what are you going to do? Go in the lab and you go, all right, this shouldn't be too hard. I know the definition of molarity. Here's the solid lead nitrate on the counter. I got water. I need to make a molar solution. Well, here's 3 definitions that are going to prove helpful. First of all, that one. If I algebraically rearrange this, and I want to isolate and solve for moles, what is moles equal to? Concentration times volume. That's super helpful. You're going to use that a lot. And then lesser known or lesser used is if you want to solve for volume algebraically, what do you do?
Moles divided by
Moles over concentration. All right, those 3 things. If you can't deduce those or derive those algebraically, write them on your 3x5 card. Well, I think one of those 3 would be super helpful in this situation. I'm going to make 1 1/4 liters of 0.85 mole of this stuff. How am I going to do that? I think I would like this equation initially because that would tell me how many moles of the stuff I need, right? Wouldn't it? And then I can take moles of the stuff I need and then figure out what? Grams. Okay, so moles is going to be the concentration times the volume. What's the concentration? 0.85 molar, which is moles per liter. And the volume is what? 1.25 liters. So now when I multiply these together, what cancels out?
the liters.
The liters. So you can see how the algebra of that one works. Somebody with a calculator, what's 0.85 times 1.25? 0.0625 moles
Or
of
one.
the, what's that?
1.06.
Oh, 1.0625. So let's say that's, I've got two sigmas, 1.1 moles of the PbNO3. Now what would I have to do for that information? Right, so 1.1 moles of lead nitrate takes me from what I can't measure and I can't count out to something that I can measure and I can count out, which is grams. Where do I get these numbers?
Periodic table.
Molar mass on the periodic table, whatever that molar mass is, it really doesn't matter what that number is, it gives me grams. Okay. So then, I got that grams, how am I actually gonna go in the lab and make the solution? I don't know what the number is, but let's just say we came up with a number like 4.7 grams of lead nitrate I need. What am I gonna do with that 4.7 grams of lead nitrate?
Put in 1.25 liters of water.
Okay, but that's the whole volume of the solution. So what you'd have to do is you'd have to get a flask, right? You have to put your grams of stuff in there first, because that's gonna take up some volume. And since molarity is moles of solute divided by the liters of the entire solution, that solid is gonna take up some room. So what you have to do is you gotta put the solid in there first and add enough water to equal a total volume of what?
1.25.
1.25 liters, which is gonna be some number less than 1.25 liters, right? You don't wanna just add 1.25 liters in, because then it's gonna be more dilute than what you actually wanted. So you have to recall that, you know, I think one of the essay questions I like to ask on this unit is, how would you make this solution? And people can usually do the math, but then where they fall short is they can't describe that you would put the solid in this solution and add enough water to equal 1.25 liters of solution. All right, there's also dilution problems. This is probably the hardest math that biologists do. There's a dig on biologists for you. You know, there's a pecking order in science, just like there is in medicine. And physicists are at the top of the block in terms of science because they have the most math. And I heard a physicist say once, well, teaching physics without calculus, you really don't understand the true essence of physics without calculus. Okay, whatever. You get to get chemistry without calculus, so we're below the physicists, and then the biologists and the geologists are down below us because they don't use much math. So the biologists like to make dilutions. You ever made a serial dilution in biology class? You take something and you dilute it by a factor of 10, dilute it by a factor of 10, and dilute it by a factor of 10. It's called a serial dilution, like a serial murderer, right? It's a serial dilution. To do that, you used to have this idea of the molarity times the concentration. Actually, you know what? Molarity times the volume is equal to molarity times the volume. This is the concentrated versus the dilute. Alright, so when you're making dilutions, this is a whole lot of what you do in the chemistry lab. You get a concentrated solution and you need something that's more dilute to figure out how much water you're going to add based on how much stuff you need. So these are the values for whatever it is that is the dilute. This is generally what you want, right? And these are the values for the concentrated, the ones that what you have, right? Alright, so say for example, I'm doing a lab of acids and bases with my students, and I walk in and I need some hydrochloric acid dilute. And what we get it shipped to us in is generally 6 molar, which is super concentrated. You put this on your hand, your skin's going to start to dissolve. So it's pretty concentrated stuff. But I don't need anything quite that concentrated. I need something that's about a half molar. So I need, this is what I have. I need half molar, and I'm doing a pretty big lab. So say I need 3,500 milliliters of stuff. No, we'll say we need more than, we'll say 350 liters. We'll say a whole bunch of it. That's way too much. So we'll have 3.5 liters. That's even better. That's a reasonable amount to use for a whole set of lab students. Okay. Well, I gotta do M1, and let's talk the algebra why this works. Molarity times volume. What are the units of molarity?
Moles per liter.
Moles per liter, right? What are the units of volume?
Liter.
Liters. All right, when you multiply those two together, what cancels out?
Liters.
Liters. When you make a dilution, you take some aliquot, some sample of the concentrated solution, and you take it out of the bottle, and then you dilute it. So what that means is whatever moles you took out of the original concentrated solution, that number doesn't change, because when you set these two equal to each other, right, moles has to equal moles. So the moles doesn't change, you're simply making it more dilute. And that's why this expression works algebraically. So now that we know why it works algebraically, let's plug our numbers that we've got in here. What numbers would I plug in to figure out what I would do to make this solution? What's the concentrated side? 6 molar, right? And what's the volume of the concentrated? We don't know that. We got to figure that out, right? That's our unknown. Right? Like in algebra, they always call X. Here's a good algebra joke for you. Have I given you my algebra joke yet?
No.
Okay. Hey, algebra. We don't know where your X is, right? I was asking you to find X in algebra. Hey, algebra. We don't know where your X is, and we don't know why she left. X and Y variables. Nice. Okay, that's a bad algebra. I used to be an algebra teacher. All right. A little humor helps to break the tension in a situation, and calculations are always tension-filled, so there's my joke for the day. All right, what's the molarity of my dilute? 0.50 molar, right? What's the volume of the dilute? 3.5 molars. All right, I think you can use this little simple algebra to solve this, right? How would you use some algebra to solve this? Divide both sides by
6.
6.0, right? And what does my number come out to be? How much was my number? 0.292? Okay, 292. What are my units here?
Liters.
Liters. All right, so now tell me how I would make this solution. Because this is going to be the question on the essay portion of the test. You can do the calculations unless you can verbally tell me or write an essay about how you're going to make the solution. What are you going to say?
0.292 liters of.
Or I'm going to take 29.2 milliliters. And what am I going to do with my 29.2 milliliters of my concentrated acid?
Put in a flask.
Pour it in a flask. And what am I going to add to the flask?
The
Enough
rest
water
water.
to equal 3.5 liters.
There we go. Not 3.5 liters of water, but enough water for the total volume to equal 3.5 liters after I add my 29.2 milliliters, right? Okay, we're all good.
Wait, we're going to I'm sorry.
Okay, so the number that we just figured out was the volume of the concentrated stuff that I need, right? I knew the molarity of the concentrated stuff, I just didn't know how much of it I needed to take out of the bottle to make the more dilute stuff, right? I did the math, I figured out I needed to take this much, which is the same as 29.2 milliliters, which is easy to measure. I would take 29.2 milliliters of the concentrated acid, right? I would pour my 29.2 milliliters of concentrated acid into a flask, into a flask, and then I would add enough water to equal a total volume of 3.5 liters, right? Okay, that's how you would make the solution. I'm very into the pragmatic part of chemistry. People can do all kind of calculations, but unless they understand what that means and how you could actually translate that into real-world examples and problems that you have to solve, then it really doesn't help much. And finally, we get to stoichiometry involving these kinds of things. Whoop, whoop. All right, let's do some stoichiometry. Hot diggity dog. This is my favorite stuff. I love math. Math is my thing. All right, so let's try one that's a precipitation reaction. We'll say lead nitrate, aqueous solution, potassium iodide, aqueous solution. I'm going to get some potassium nitrate, which we know is going to be aqueous because nitrate is always soluble. And then I'm going to have some lead iodide, which is my solid. Now to balance this, I need a 2 there and a 2 there. Gets me where I need to go. So, for example, say I'm starting with 25 milliliters of this stuff and it's a 0.3 molar solution. And I got 40 milliliters of this stuff and it's a 0.2 molar solution. I want to know what's the mass of the solid I can make based on my starting quantities. First of all, is this going to be a limiting reagent problem? Just knowing what you know and based on my description of what I just wrote down. Is this going to be a limiting reagent? Yes, it is. How come? How do you know that? So you got two, right, you need coefficients, but you also got two different reactants, and one of them's going to run out first, right? Alright, so what can we do with information like volume and molarity that
Find
help
out moles.
get moles? And moles is equal to what? Concentration times volume, right? So shouldn't I just do that? So I can figure out how many moles of the lead I have. So the moles of the lead would be the concentration, 0.3 molar, times the volume. In this case, I want to use liters, so that's 0.025 liters. Somebody with a calculator, what's my concentration of my lead nitrate? What's 0.3 times 0.025? 75 moles of the lead nitrate. Alright, we're going to do the same thing here. We're going to take moles of this stuff is equal to the concentration, 0.2 molar, times the volume, 0.040 liters. So that would be 2 times 4, 0.008? I think that's what it is, 0.08, right?
Yep.
Moles of Ki. Alright, so now let's look at a VCA. I've got this many moles of my lead compound, 0.0075 moles. And I've got this many moles of my other stuff, my potassium iodide, using the equation here to bring down to my VCA. The Ki, I have 0.008 moles. Well, I got more of this stuff than this stuff, but what does the balanced equation tell me? Who gets used up at a more rapid pace?
Ki.
The Ki does, it's 2 to 1. So I would bet which one is going to get used up all.
Okay.
Probably all the Ki, so minus 0.008 moles. I'm not going to have any of that left over. If I use up 0.008 moles of this, how much of this will I use up?
This divided by 2.
By 2, so I think that's 0.004. Right, you're subtracting 0.004, so that gives me 0.0035 left over. I think that's the math of it. Alright, so now, remember we gotta look at the change, figure out what's being generated. So if I know that this is 1-to-1 ratio, and I used up 0.008, how much of this should I generate? 0.008, so 0.008 moles I made, 0.008 moles at the end. And this one, since it's 1-to-1, am I going to use 0.0075 or am I going to use 0.004? 0.004. So I start out with 0 there. I'm going to generate 0.004. I'm going to have 0.004 moles at the end. Alright, if I want to know the mass, how would I figure that out? There's the mass of the stuff, 0.004 moles of PbI2, right? Moles PbI2 to grams PbI2, whatever the mass is, bless you. So now it's just a matter of connecting stoichiometry to stuff that you know and stuff that you're learning. So this is going to be the same kind of thing. Now you need to incorporate concentration into your calculations. And if you like the stoichiometry flowchart, remember stoichiometry flowchart, grams, number of particles and concentration, gets you to moles of the first thing, which then you can translate to moles of the second thing. And you can go back and forth. And the number that gets you here is the molarity. So that's what we've added. If you're looking at stoichiometry flowchart, that's the piece that is now being added to our framework. All right, you got lots of homework due, lots and lots. I'd get it, you know, you could probably finish this one too. If I were a student in this class, I'd finish homework 5 also over the weekend and get ahead of the game, even though it's not due till Thursday.
I'm sorry, Laura.
Yes.
What was the original question for that one?
The original question was, yeah, how many grams of this stuff could you make?
Okay.
And usually a problem will give you that. They'll give you the volume and the concentration of reactants, and then they'll say, you know, how much gas could you generate, or how much solid could you